Okay, 4.1 day 1, we start talking about exponential functions. So our objectives for this lesson are we're going to evaluate exponential functions and we're going to graph them. So we first start out with the definition of the exponential function. It says the exponential function f with base b is defined by f of x equals b to the x or y equals b to the x, where our b, our base, is a positive constant other than 1, so our b is going to be greater than 0 but it cannot equal 1, and x is going to be any real number. Alright, so you notice on both of these, the only difference is they replaced f of x with y, which we know is the same exact thing. But on both of these, where is your x? Your x is up in the exponent, and that's what makes it an exponential function, is the fact that your x is in the exponent. Alright, so they start us out here with this word problem, and it says the exponential function f of x equals 42.2 times 1.56 raised to the x models the average amount spent f of x in dollars at a shopping mall after x hours. What is the average amount spent to the nearest dollar after 3 hours at a shopping mall? Alright, so we've done word problems quite a bit this year, and so we know if they give us an equation, it's probably pretty important. So I'm going to bring out that equation. And so I need to make sure I understand what these variables represent. So f of x, so I'm going to look back up here and I see where it's talking about f of x, and it says it's the amount spent in dollars. So this is just our amount spent. And then the other variable we have here is an x. And so we can see where it talks about x, it says after x hours. So x is going to be the number of hours. Now let's go back to the question. So the question says, what is the average amount spent? What is the average amount spent? So this is what we're after. So we're after f of x to the nearest dollar after 3 hours. Now they didn't write 3 as a digit, they wrote it out in words, but there's our number. So what is that 3? Well, the 3 is an hour, so it has to be our x. So we're going to find that f of x, or you could put f of 3 there if you wanted to, but so we're going to plug in x is 3 over here, and we're going to solve. Alright, so when I do this, I get like 160 point, I think it's 20 something, okay? So I just cut it off there, because when I look back, it tells me it wants me to round to the nearest dollar. So I have to look at that 2. What is that going to make happen to the 0? It's going to make it stay the same. So we end up with $160. All right, in example 2, we're going to graph this. So we're going to make ourselves a table like we did back when we did the other graphing, back in chapter 2. And so in my table, I'm going to have a column for my x's. And then I'm going to make myself a work column. I have a column for my y's, and then I'm going to go ahead and write it as an ordered pair. So it's easier to graph because I can see it. Now remember when we did graphing before, we always use the values -2 to +2 unless our equation had a radical in it, so like the square root of x or the cube root of x. Well, this one doesn't, so we're going to do the same thing, so -2 to +2. But now because the way this is set up, I am going to go ahead and start at the bottom of my table. Excuse me. So we're plugging this into 3 to the x. And so at the bottom of my table here, my x is 2. So I have 3 to the 2, which 3 squared is 9. And so when I write it as an ordered pair, I got my x and y, so my ordered pair is going to be 2, 9. Working my way up, 3 to the x. This time my x is 1. 3 to the first is 3. And so my ordered pair is going to be the xy, which is 1, 3. Then we have that 3 to the 0. Now be careful because that has a special rule. Remember, if your exponent is 0, your answer is going to be 1. Alright, and so we have the ordered pair, x is 0, y is going to be 1. Now, when we have 3 to the -1, we don't like negative exponents. So we talked about this a while back, but we're going to send it to the bottom, so it becomes 3 to the +1 on bottom, and you put a 1 on top. And so you get 1 over 3 to the first, which is 3, so my y value is going to be 1/3. So my ordered pair is -1 and 1/3. And then we're going to do the same thing with that 3 to the -2. It's a negative exponent, so I'm going to send it to the bottom, which is going to make that 2 positive, because anytime an exponent crosses a divide line, it's going to change the sign of it. So if it's negative, it becomes positive. Positive would become negative. And if there's nothing in front, nothing else written, we always put a 1 on top. And so we get 1 over 3 squared, which is 9. And so my ordered pair is my x was -2 and my y was 1/9. Now, if you notice, as we go up the y column there, our numbers are getting smaller and smaller and smaller, but they're never going to be negative. So if I kept going, if I said x was -3, I would get 1/27 as my y value. If x was -4, I'd get 1/243. My number's getting smaller and smaller and smaller, but it's never going to be negative. And that's because exponential functions have what they call a horizontal asymptote. And it's going to be at y equals 0 for parent functions, okay? So horizontal, of course, means it goes left and right. An asymptote is a line that our graph will typically never, ever, ever cross, okay? Now, if it's a vertical asymptote, meaning it's going to go straight up and down, and we'll talk more about that in 4.2, we never cross it. Never, ever, ever cross a vertical asymptote, okay? Then they have what they call a slant asymptote, which we're not going to talk about probably this year. But a slant asymptote, it typically does not cross it. It just gets really super close to it. Now, horizontal asymptote, some graphs will cross a horizontal asymptote only near the origin, okay, in the middle there. But for our purposes, for the exponential functions never cross a horizontal asymptote. They're just going to get super duper duper close to it. So close that if I'm graphing it on the calculator, it will actually look like my line becomes that line, my exponential function will become that line, or that my graph would just stop. And that has to do with the pixels that are on that calculator. All right, so first thing we're going to do when we go to graph this, though, is we're going to graph the horizontal asymptote, which is at y equals 0, which is also the x-axis. And so an asymptote is always drawn as a dashed line. And so I'm going to draw in this dashed line here, which is a horizontal asymptote, and it's at y equals 0. And so I usually abbreviate the asymptotes. HA is horizontal asymptote. You'll see in the next week that VA is our vertical asymptote. And if we did a slant, I would just label it SA, just abbreviate it to help us out. But I labeled it here so that if you look back later, you'll be like, oh, okay, I know why that dashed line is there. Then we're just going to plot our other points. So we got the point -2 and 1/9. So I'm going to go to the left 2 and up 1/9. Now I don't know exactly how far up 1/9 is, but I know it's between 0 and 1, closer to 0. So I'm just going to estimate it and do my best there. Then I got -1 and 1/3, 0, 1, 1, 3, and 2, 9. Now when I graph this, it should be a smooth curve, so I'm going to do the best I can. Okay, now when I graph it going to the left there, I'm going to graph going towards that asymptote, but I don't want to cross that asymptote, okay? So that line is actually not getting straight. It's just slowly going down. But it is getting closer and closer to 0, but it's not going to cross it. All right, now before we move on to the next slide, if you printed out your notes, you can write this down at the top of them. If not, you might want to grab you an extra sheet or something here. All right, so back in lesson 2.5. I wrote, and I told you you could put it on the back of your notes, so I'm not sure if you did or not, but if not, you can rewatch the video. From 2.5, we talked about transformations, and we looked at different equations, and one of them was this one, the quadratic. All right, and we talked about in specific what the A, B, H, and K did. And I told you it works on every single parent function. Well, it works on exponentials as well because it's a function. In exponentials, it's going to look like y equals a times. Now, they're going to have some number here that is our base, okay? That's not the a, b, h, or k at all. It's just a number that's a base. We saw in the previous one it was a base of 3. You could have a base of 2. You could have a base of 10. You could have a base of 1/2. Remember, you can have any base that's greater than 0 but not equal to 1. All right, and then it's raised to the bx minus h, and then we have that big plus k there. And so just a quick review real quick here. Remember we had said that A was our vertical stretch or compression, B was our horizontal stretch or compression, H was our horizontal shift left or right, and the K was our vertical shift up or down. Now remember the A and the k are not up with the x, those affect the y values, and they do what they're supposed to. So it says a times the base, so I'd multiply my y by a. It says at the end plus k, so I would add k to my y's. But remember good old x up here. X, whether it's trapped inside parentheses, trapped inside absolute value bars, underneath a radical, up in the exponent like it is here, everything with x does the opposite. So it says x minus h, so we will add it. It says b times x, so we would divide. Everything is opposite, including PEMDAS. So if you don't remember this, you're going to want to look back at those 2.5 notes or rewatch the video where I talk about it. All right, so back to our other notes then. All right, so it wants us to use the graph of f of x equals 3 to the x, obtain the graph of g of x equals 3 to the x minus 1. Well, notice the base is still a 3, which just tells me that the table we saw in the previous slide is my parent function, okay? Unfortunately, exponentials are not like quadratics or cubics where they have one parent function every single time. We have multiple parent functions because your parent function will change on an exponential every time that base right there changes, okay? 2 to the x will have a different parent table. 1/2 to the x will have a different parent table. So anytime you have a different base, you need a new parent table. So here we can look at this, and the only difference we have then is we have that x minus 1. So in words, what would that do? Well, using my vocabulary, that is that h value. So it's going to be a horizontal shift, and we always tell direction and the number. And so a minus 1 is going to go to the right, because remember it does the opposite, 1. Now, I'm just going to jot down real quick here my table that I had in that previous slide. Now, if you have the notes, you can see your table. But I want to write this down so I don't make any little mistakes. And so this is the table that we had come out with in the previous slide. And so now we're going to use our transformations to graph our new graph. Well, we can see, looking at the problem, it says x minus 1. And we know with x we always do the opposite. So I'm really not going to subtract 1. We're going to add 1 to our x's. Now there's nothing in front that's the same size as a 3. There's nothing at the end that's the same size as a 3. So therefore there's nothing that's going to affect those y values. So my y values are going to stay the same this time. And so we're going to take all of these x values here and we're going to add 1 to them. So negative 2 plus 1, negative 1 plus 1, 0 plus 1, 1 plus 1, and 2 plus 1. My y's are staying the same. And then the only thing that I didn't put that we can't forget is remember that the parent function always has a horizontal asymptote at that y equals 0. Now notice it's a y equals. So anything that would affect my y's up here will affect that horizontal asymptote as well. Well, nothing affected my y's, therefore my horizontal asymptote stays the same. But, just as a little thought here, if up here I would have had y plus 1, then my horizontal asymptote would be at y equals 0 plus 1, which would have been at y equals 1 then, okay? So whatever you do to your y's, you're also going to do to that 0 that's your horizontal asymptote. But we didn't have that in this one, so this doesn't apply. We didn't change anything on the y's, so we don't change the horizontal asymptote. All right, so I'm going to go to graph this just like before. I'm going to start out with my horizontal asymptote. I'm going to plot, I'm going to plot my points. And I'm going to connect them. Just make sure when you graph it, you don't cross that horizontal asymptote, okay? Now, looking at that, it looks like my graph is going straight right here, but is it? It's not. It's slowly, very, very slowly getting closer to that line y equals 0, but it's never going to cross it or touch it, okay? So it's just slowly going down. All right, and then our last slide here is just some information about it. So I'm just going to open up another slide and let's talk about it. So we're looking at a graph, if I kind of just sketch what I just had, it looks something like this, correct? So let's talk about its domain. Does my graph keep going to the left? It does. Does it keep going to the right? It does. Therefore, my domain is negative infinity to infinity. My range, the y values. Does my graph keep going down? It does not. It keeps going down towards a 0, but it's not going to go past that 0. So we're going to put that it's going to start at 0, but 0 is not included, because remember, that's the x-axis and we're not going to touch it. And then does my graph keep going up? Yes, it does. So it goes up to infinity. My x-intercept. Remember, an x-intercept is where the graph crosses the x-axis. On this one, guys, on the parent functions, my x-axis is that asymptote. We're not going to cross it or touch it, so it's not going to have an x-intercept. My y-intercept. On all my parent functions, remember, a y-intercept is always going to have x as 0, and then if on my parent functions, if I take any number and I raise it to the 0 power, we always get 1 as our answer. So all your parent functions are going to have the ordered pair 0, 1 in their table. Now, increasing, decreasing. Both of the graphs we looked at today were increasing, but that's because our base, that 3, was greater than 1. So if our base is greater than 1, our graph is going to be increasing. If our base had been between 0 and 1, then our graph would be decreasing. All right, so the increasing looks like what we've seen. Decreasing, it would be coming down. Okay. And then the last thing is, what about the horizontal line test? Remember, we talked about the horizontal line test. And so if I took this graph, and it doesn't matter what horizontal line I draw, it's never going to touch it more than once. Now be careful, because this section right there looks a little iffy, but remember, I specifically stressed that it's going to keep going down very slowly, but it's going down, okay? So even though it appears to be going straight, it's really not. So it does pass the horizontal line test. Which if it passes the horizontal line test, remember we had talked about that meant it's called a one-to-one function. And we talked about the horizontal line test when we were talking about inverses, which means it has an inverse function. And we're going to talk about its inverse function next week. All right, so that's pretty much what that last slide is telling you. I just kind of summed it up, went through it slowly, a little bit slower so that you could see it. It wasn't quite so intimidating, hopefully. All right, so that is the end of day 1.